Okay, good afternoon and welcome again to the Communication Signal Processing Seminar. Last week we postponed the seminar due to some other reasons, but I'm very glad to have Osman Yagan today here present, be the speaker. Osman is an associate research professor at the Electrical and Computer Engineering Department at Carnegie Mellon University, so our sister university in Pennsylvania. Prior to joining the faculty of this department in August 2013, he was a postdoctoral research fellow in CyLab at CMU. He's also held a visiting postdoctoral scholar position at Arizona State University during 2011. He received his PhD degree in ECE from the University of Mellon at college in 2011, and he had his bachelor's degrees in electrical and electronics engineering from Middle East Technical University in Ankara in 2007. So Osman's research interests are in modeling, design, and performance evaluation of engineering systems with particular emphasis on communication systems and networks. His specific research topics include wireless communication, security, random graphs, social and information networks, and cyber physical systems. He's a senior member of IEEE and a recipient of CIT Dean's Early Career Fellowship. So before he takes the stage, I just wanted to thank KLA, who's a sponsor, and also the two research groups, NCIS, which is Networks Communication Information Systems, and SIPML, which is Signal Image Processing and Machine Learning. All right, Osman, go ahead. The floor is all yours.
Thank you so much, Vijay. Thank you, everyone, for the invitation and for attending. Today, I'm going to talk about our work on multi-arm bandits with structured and correlated arms. This is joint work with my colleague Gauri Joshi, our joint PhD student Samarth Gupta, as well as with Shriyas Chaudhary and Subhajyoti Mukherjee. And we acknowledge the support from various agencies, including NSF and some industry sponsors. Let's go back and start from the classic multi-arm bandit problem as an introduction. So in the classic multi-arm bandit problem, we have a sequential decision-making.
Osman, 1 second, just 1 second. So I mean, I see there are, so in terms of the guests, can you actually put your name and please don't have XYZ guests because we don't know. I mean, this is a department seminar, so I do want people's names to be there. Sorry to.
Oh,
it's
sure.
Supposed to be a totally public one, right? Yeah. Thank you. So because there are certain people that names are XYZ guests, so I just want to make sure I actually have a name of the person there. Thanks.
Oh, you mean on the
participant list? Yeah.
Okay.
Anyway, go ahead, please.
Oh, sure. So this is a sequential decision-making problem where at every round, we are going to choose one of these K arms. And upon choosing an arm, we receive a random reward associated with the probability distribution of the corresponding arm. So if I choose at any point throughout this game, I choose, let's say, arm 1, I receive a random reward following the distribution R1, or R1 is a random variable that is going to be an instantiation of that is going to be the reward I receive upon pulling arm 1. Similarly, if I choose arm 2, I'm going to receive a random reward following this distribution, and so on and so forth. And before we start this game, there is no prior information about the reward distributions. And of course, if you don't know the distributions, the mean rewards of the arms are unknown to you. And the goal, the particular goal in this setup that we are considering is the maximization of the expected cumulative reward. So let's say we are told that we will play this game for T rounds. The goal is to come up with a mechanism to leave these T rounds with as much reward as possible. The goal of maximizing the cumulative reward can be equivalently posed as minimizing the expected regret. And regret is basically defined as the reward that we lose by making suboptimal decisions. So let's say K star denotes the best arm, best in the sense of having the maximum reward, maximum mean reward among all these K choices. The argument is that if you knew which arm had the highest mean reward, you would have picked it in all of the T rounds, and you would have basically obtained T times VK star as the total reward. And your regret is how much reward you lost, or how much less than the optimal you obtained by choosing occasionally maybe not the best arm, but one of the suboptimal arms. So this problem is naturally a good fit for modeling exploitation trade-off. And you can see that any application where you have the trade-off between either exploiting the current best action, so the action that has been performing the best so far, versus exploring maybe the actions that are just introduced, or the actions that you don't have enough samples from. Whenever you are in this dilemma, multi-arm bandits could be used as a modeling framework, and it can the algorithms designed for multi-arm bandits can be the appropriate solution. This is actually being used in various applications, including clinical trials, to find out the best dose of a drug, or to find the best treatment for a maybe unknown disease or a new disease. Heavily used in web optimization to find out how to design a website, where to place the advertisement, and also which advertisement to show to each given user. And in that context, it has also similarities or relevance to recommendation systems. So throughout, we will see a picture like this. So I wanted to show this ahead of the time. So the classical example we'll go through is either ad optimization. So for a given user or a pool of users, the question is which advertisement is most suitable for them, or also you can view this as movie recommendation, which type of movie or which specific movie is the most relevant or most likely to be viewed preferably by a given user. You could view this as a bandit problem. And in the classic bandit setting, what you have is an anonymous user. So you have no information about that. You don't know if they will be liking a specific movie like this, or a movie from this genre, or whether they will be liking, I don't know, a drama like Joker, or something like a musical like Bohemian Rhapsody, and so on and so forth. And again, you can view this as a problem where eventually your goal is to maximize the cumulative reward by sequentially showing this anonymous user that you don't know anything about, one movie or one advertisement at a time. So let's, sorry, my mouse, I think, has been disconnected for a while. So let's go back to the basics of bandits rather than the application. There are various algorithms that people have proposed and analyzed so far. And if you look at the literature, you'll find so many of them. So there's not enough time throughout this talk to talk about every single bandit algorithm. But the most popular algorithms you will see are UCB, upper confidence bounds algorithm by Auer et al. There's Thompson sampling algorithm that has been around for a while, but its regret analysis has relatively recently been completed. And there's also KL-UCB by Bubek et al. That has received quite a bit of interest, and it has, in some cases, has been shown to be the optimal algorithm, or its performance is shown to be matching the regret lower bounds that have been known for a while. And although these algorithms, the mechanics are different from each other, what you will see in all of them at a high level is the following result. So in the bandit case, with K arms, one of the arms is optimal. Any one of them could be optimal, which means that there are K-1 suboptimal arms. And the expected regret in all these algorithms turns out to be K-1 times log T, at least in terms of the order of the regret. What this essentially means that out of the K arms, one is optimal, each of the remaining K-1 arms is being pulled order of log T times. One way to put it is that although the frequency of suboptimal choices decreases over time, you never stop making suboptimal decisions. Actually, each of the suboptimal arms are being pulled infinitely often in this setting using these algorithms. so this is a result that we will sort of remember and compare with maybe what type of results we get under maybe more general bandit cases or specific bandit models we are considering. And these models that we will talk about today are motivated by the fact that the classic setting, although quite nice, has some limitation. And this limitation is mainly about either implicit or explicit assumption that the rewards from different arms are independent from each other. So to see this as maybe a drawback or maybe not quite fitting the reality, we can remember the movie recommendation application. And actually people have looked at this model and realized that the classic bandit setup is not quite right. And instead they came up with a variant called contextual bandits. And this is especially suitable for personalized recommendations. And what happens here is that when a user joins in, as happens in social media or as happens in maybe some of these movie platforms like Netflix or you know, Hulu and so on and so forth, the user comes with some information associated with them, right? So this is called the context in this setting. Maybe you know their age, you know their maybe occupation, their zip code, browsing history, depending on how much data these systems are collecting. And the idea in the contextual bandit is that before making a recommendation to a user, you first see their context, you know that, and then choose one of these maybe actions or show them one of these movies or show them one of these advertisements, basically. What you don't know initially in the contextual setting is how these contexts are mapped to the mean rewards of different actions. And the idea is over time, as you see the context and the corresponding feedback from maybe your different actions, you get to learn these mappings. So you get to know maybe which age and occupation payer returns what kind of reward for this movie or for this advertisement, and similarly for all others, and eventually get to do the best possible personalized recommendation for each given you know, age, occupation, payer, or other context. You can basically recommend the movie that they will like, you know, with highest probability or with the highest utility, whichever utility definition you are using. Today, we will again be looking at two different variants of the classic bandit setting, and they will be using different motivations and actually different models. The first one I'll talk extensively about is called structured bandits. So I'll talk about it in details, of course, but this is quite similar to contextual bandits, except that what is known and what is not known have been swapped. So in the contextual case, you were seeing people's private information, but you didn't have any idea about how this private information may be mapped to different movies, and you wanted to learn that over time. In the structured bandit case, the problem is switched in the sense that you are doing, in some sense, a privacy preserving recommendation. So you don't want to know people's private information. So the context theta here is unknown, but you know a priori the mapping from the context to the mean rewards of different arms. And we'll talk about maybe how we can acquire this information and try to motivate that this you know, has valuable consequences or valuable place in the application domain that we are considering. The second problem is different. We will talk about this one as well. We call this correlated bandits. So the structured bandit case has been also studied in the literature. So we are by no means are the inventors of this. So throughout we will talk about how our algorithms or assumptions compare with the literature. But this particular correlated bandit setting is relatively new. To the best of our knowledge, in this particular way has not been studied before. And here what we say is that I'm dealing with a population here, not just one user as in the structured case. So I have a population of users. I take them one at a time and get to recommend them one movie, and then I lose that user for good. And I like to sequentially basically take this user, make my recommendation, and move on to the next user, and so on and so forth. The assumption is that I have no information on the user context before I make my decision. I also don't know the distribution of the context. So I have no distributional knowledge about this population either. But what I will try to leverage in the correlated bandit case is the fact that these items that I am showing to them are inherently similar, or there's some inherent correlation among them. So if I am picking this particular user and showing them a specific movie or showing them a specific ad, upon observing the reward from that, I can maybe make some estimation on how much reward I would have obtained if I had shown them this movie, or how much reward I would have gotten if I had shown them this movie. So with some prior loose, but some prior information on such correlations, we are trying to improve the cumulative reward of the classic bandit setting in this correlated bandits model. So there will be these two extensions that I'll talk about, and I'll talk about what algorithms we have sort of proposed for that, and what are the performance results associated with that. So today's outline will be on these two models. Okay.
Hey, Osman, can I ask a quick question?
Sure, of course.
Yeah, so for the second case, do we assume each time the user is picked from the same distribution? So like
yes.
Okay, thanks.
Right. Yeah, that's a good one. Good point. Yeah, we are assuming that the correlations or the joint distributions stay the same. We don't have the joint distribution information, but the assumption is that they are coming from the same population. And one way to sort of do it is if you have an actual population, you could do a random selection and then make sure that actually they are coming from the same distribution that way. Could be like one general high-level joint distribution, and as long as you make your selections uniformly at random, that will be preserved. But we can discuss further, I think, the technical parts.
So
sure.
just Osman, another question there. So it seems like in that case there is some parameter of the joint distribution that you don't know, and that's what you basically are. That's chosen ahead of time, and in some sense, that's a way to think about it, right? Or
right. So you don't know.
Like for example, it could be Gaussian. I mean, there could be Gaussian distributed rewards, and I don't know the covariance function, for example, right? I mean, that's another way of thinking.
Right. Our model is a bit more general than that. It's basically, so the only thing I'll talk about the model a bit towards the end of the talk, but it's basically saying that I know the upper bound on the conditional expected rewards. So I know if this movie has been ranked, let's say 4, this could have been ranked at most by 3 out of 5. But again, it's a sort of upper bound on the average rating. Doesn't have to hold for every single user. So I'm basically saying that somebody who likes this cartoon, this kid movie, couldn't have given more than 4 out of 5, or the average user doesn't give more than 4 out of 5 to this, I don't know, horror movie or things like that. So that's the only assumption we will be making. But as you said, that type of setup is also quite similar, right? Assuming that it's jointly Gaussian, but some parameters are unknown. So
okay, thank you. Yeah,
sure. Okay, so let's start with the structured bandit case. So as I mentioned, this is the contextual bandit-like setting, except we don't have the context. So it's a hidden context version of the contextual bandit. But what we assume known is now the mean rewards of different arms. So I don't know the user's context, but I know as a function of that how what is the mean reward of this arm and this arm and so on and so forth. Let's look at the general setting that we have sort of set up here. So the unknown parameter, the latent parameter theta, lies in a set. And that set can be discrete or uncountable. So both continuous and discrete theta cases are included in our framework. And the unknown latent parameter doesn't have to be a scalar, it can be a vector as well. And again, mean reward of arms are known functions of this, this latent parameter theta. And other than that, we are not making any assumption on the mapping being linear or invertible, or any such assumption is not included in our framework. The goal is again to maximize the cumulative reward by sequentially choosing the one of the K arms.
Hey, Osman, I have
Sure.
another quick question. So since
Yes, sir.
theta assume here, the theta assumed to be fixed. So there any difference, I mean, assuming it's a scalar or it's a vector, they're all same, right? Then change the problem.
Right. So it changes the problem a little bit in the sense of right. Yeah, it doesn't really change much. You are right. It's just that maybe from a application perspective, it makes it a little bit more fitting to cases where maybe not only one parameter, but you want to know more than one attribute of the user, more than one feature of the user. But yeah, from the problem's perspective, right, you are right. It doesn't change anything.
Okay, gotcha. Thank you.
Yeah, sure. So one question here is, of course, how do you know, or how do you motivate this setting, right? Like, okay, it's okay to, and it's even nice to not know people's private information, but how do we actually come up with these mean reward functions? And the structured bandit setting has been studied before us by several different groups. And the usual explanations or motivations for the knowledge of such functions is either, you could say, domain knowledge, like people who have experience with a field, if it is clinical trials, you know, drug dosage optimization. There may be some domain knowledge about which type of maybe features are mapped to maybe different types of actions that we can possibly take. A better explanation or a better motivation in our mind is maybe controlled user studies. So you can collect a number of people, do a paid survey, and basically learn these mappings through these controlled studies. And the second maybe explanation could be using contextual information from a previous campaign. And the idea here is that these companies, social media companies, or you know, movie platforms, they've been collecting data for a very long time. If for some reason from here onwards they are forbidden from using user data, they could still basically go back and learn these mappings. They already know these mappings for all we know. And in the future, they could still be using a structured bandit-like setting to make recommendations to people, even though they don't necessarily know their features anymore. So that could be another way to motivate this type of a problem. So again, either domain knowledge or a paid survey, an offline study, or something that you have known from previous campaigns could be leveraged to sort of assume that, or could be leveraged to get these mappings from the user context to the mean reward of arms. So the question is how we can leverage this information. And people have actually looked at it, as I mentioned, quite a bit under different assumptions. So one common assumption is that these mappings have to be linear. So the mapping from the user context to the mean reward of each arm has to be a linear mapping with known weights. So that's very commonly studied. There is a GLM, generalized linear bandit version by Felipe et al., where they said the mean reward mappings are a function of a linear function of theta, but that function is invertible. And there are other variants where, again, the invertibility of these mappings have been imposed. And if you think about it, if these functions are invertible, you kind of simplify the problem quite a bit, because anytime you get a large number of samples from an arm, you have a good idea about the empirical mean, which is supposed to be in most cases close enough to the maybe the actual mean of that arm. And if this function is invertible, that gives you a good idea about what the actual theta is. And if you know the theta, the problem is basically solved. So invertibility assumption in our opinion, is a bit too strong, and it simplifies the problem, makes it nice maybe, but also reduces its applicability. There are works such as this one cited here, where they are assuming that not only this mean reward as a function of theta is known, but they go further and assume that the conditional reward distributions are also known, which is also an interesting problem. It puts it into more like a Bayesian optimization setting. And you know, these works are very valuable, but in our case, we wanted to not go to that extreme and simply assume that the mean rewards are known. So the distributional knowledge in our setting is assumed to be not available. So once you get rid of the invertibility assumption or linearity assumption of these mappings and the assumption that conditional reward distributions are known, there are not that many works left in the literature actually in the structure setting. The closest one that fits into those cases is by Latimore et al. In 2014. And they basically came up with a algorithm that extends the UCB algorithm to the structure setting. And as you may have guessed, they called it UCBS, S standing for structure. So throughout, we will constantly compare our results with the UCBS algorithm. So the closest competitor to our approach is basically that one. So let's look at what is the main contribution of this line of work. So it's collected in a paper given here, and it's currently under review, where we proposed and analyzed not one algorithm, but actually a class of algorithms for the structure setting. And again, this is done without any linearity or invertibility assumption. We call our algorithm class or set of algorithms as algorithm C, C standing for competitive, and I'll talk about what competitive mean in this setting. But basically, this is a setting where we could be using any current or future classic multi-arm bandit algorithms, such as UCB, Thompson sampling, Cal, UCB, and etc., and something that isn't being even introduced yet. And we are providing a way to convert that algorithm to the structure setting. So if you want to use UCB-like algorithm for the structure setting, we have a way of doing that. But instead, if you want to use Thompson sampling-like algorithm, which usually performs better empirically, we provide actually a way of converting Thompson sampling to be suitable to the structure setting. And in that case, the algorithm is called TSC. And similarly, again, for any algorithm. And this is in contrast with the Latimore's approach, where they were able to only extend the UCB-like algorithm to the structure setting. And the work we have done here is actually also motivated by the Latimore's work, where after providing this algorithm, they argued that it's going to be much more interesting to see other extensions of classic algorithms to the structure setting. But so far, they couldn't see a way of achieving that. Especially, they motivated the reader of the paper by saying that it would be nice to get a Thompson sampling-like extension to the structure setting. So the work here is basically motivated by that, and to the best of our understanding, we accomplished that goal set forth in the paper by not only extending the Thompson sampling-like approach, but any, again, classic bandit approach to the structured setting. So let's look at what kind of results one can get under this setup. So if you remember, the classic setting tells us that there are k arms, one of them is optimal, and each of the remaining k-1 arms, you will be pulling them in order of log t times. So each suboptimal arm, you keep pulling them infinitely often with decrease in frequency, so that you end up, if you play this game t rounds, you end up pulling each suboptimal arm roughly on the order of log t times. For the algorithms that we propose, this is not the case. More precisely, what we achieved is that instead of pulling every single suboptimal arm log t times, we are only doing that for the arms that we deem as competitive. I'll define what that means. But the arms that we deem as non-competitive are going to be pulled only finitely many times, only order 1 time. What this means is that our algorithm starts in the usual way, but at some finite point is reached, after some finite point is reached, some of the arms, some of the suboptimal arms have being stopped, basically being from pulled. So they will never be pulled after some finite time is reached. And the number of competitive arms can be as large as k. So all suboptimal arms can be competitive technically, in which case our results will match the corresponding UCB or Thompson sampling algorithm that we are trying to extend. But in the best case scenario, only the optimal arm will be competitive, which means that if C equals 1, our algorithm is going to get constant regress. So there are cases where the algorithm is able to stop pulling any suboptimal arm in finite time. So after a finite point is reached, only the optimal action is taken. So this is the high-level performance of our algorithms. Let's talk about how we achieve this. And first of all, talk about what competitiveness means. The definition is actually quite simple. If you look at just the first bullet, it basically says that we call an arm as non-competitive. So these are the ones that we stop pulling after finite time. If this can be identified as suboptimal only from the samples of the best arm. So if I give you the option to choose the best arm, you can get as many samples as you want. And from those samples, if you have enough idea about the hidden parameter theta, that lets you say, well, this arm or this set of arms can never be optimal under this theta, or when theta takes its values from this range, then those arms are actually non-competitive. Otherwise, if you cannot achieve that, that arm will be deemed to be competitive. What is probably important to note here is that the number of competitive arms or the set of competitive arms is not known a priori because they are both functions of the hidden parameter theta. So the algorithm doesn't start by this knowledge, but as it progresses, it manages to eliminate or it manages to stop pulling any arm that fits into this category of being non-competitive. So here we show an example with 3 arms with different mean reward mappings as a function of theta. And basically, there are different regions where one arm is optimal, and in this region, maybe another arm is optimal, and so on and so forth. And the number of arms competitive also changes with theta. So in this region, if theta falls between 0 and 1, there is only 1 competitive arm. Here it is 2, 1 again, 3, and 1, so on and so forth. So basically, again, the number of competitive arms is something that you can only identify or like determine after the fact, after you know what the exact value of theta is. Okay, so the algorithm is a pretty simple structure. As we said, this is extending the classic algorithm. So the last step of the algorithm will always be borrowing from your choice of basically classic bandit algorithm. And the first step is also not, unusual. Based on the samples we have so far, we are estimating a confidence set of where the actual value of the theta might be. And for each arm, using the samples you get from this arm, you get potentially a different confidence range. And what we do is we take the confidence range you have from this samples from this arm and intersect it with that you obtain from this one and intersect it with this one, and so on and so forth. So you take the intersection of the confidence intervals. And then within that confidence interval, you look at which arms have any chance of being optimal. So here I give one example where, let's say, the shaded region is at any point in this algorithm. Let's say I managed to reduce my confidence interval to this shaded region. So it's taken to be the same for all, just for simplicity. And these dashed parts here are basically telling me under which values, for this blue case, the arm 1 is optimal. So here in this region, arm 2 is optimal, and in these green regions, arm 3 is optimal. But if my confidence on theta tells me that I'm with high probability looking at a case where my hidden parameter is here, I notice that this is outside of the region where arm 3 is the optimal one. So what I notice is that if my confidence, if my theta, if my hidden parameter lies in here, arm 3 has no way of being optimal. So what I do is I freeze this. You can call that removal, but may not be quite accurate. What we do is we simply freeze this arm for this step only. So, or you can call it remove, again, only for a specific step. So whenever we say removal, it's never a removal for good. It's just for a one-step elimination of the corresponding arm, which again happens to be not optimal within the confidence region that you currently have for theta. And if you eliminate those that are non-competitive, that are not passing this criteria in the second step, you go to the third step and play any algorithm of your choice among the remaining arms. So in this case, if your confidence interval for theta is here, you decide that there is no way for the third arm to be optimal. What you do is you will play, if you are using UCB, you will play UCB among these two arms. If you are using Thompson sampling, you will do the same, and so on and so forth. So the algorithm setting is, in summary, like this. The estimation of the confidence set is quite common, leveraging the Chernoff bound. We are using a term like this to basically look at where the theta might be lying with high probability. And again, maybe what is something you may want to know is that we are using this confidence region as the intersection of different confidence regions you get from all the arms. Since this confidence region is already set forth by taking into account how many samples, so NKT is how many samples you have so far from a specific arm K, it sort of makes it a meaningful way to construct your confidence. So you may be wondering if you have so many samples from one arm versus not as many samples from another arm. That's already well taken into account with the way we are constructing the confidence interval. So, that part is sort of could be skipped, a bit fast. The step 2, as I explained, is simply saying that within your current confidence region, which arms have any chance of being optimal, and those that have no chance are eliminated for that round. In this case, again, the third arm is eliminated, and the step 3 is basically saying that you can play UCB, Thompson sampling, or any algorithm of your choice to decide between these two. Now, once that decision is made, you go back to step 1 and re-evaluate your confidence region on theta and then repeat the steps. So that's basically what the algorithm is doing. So the results that we obtained for the regrets are given in 2 theorems. The first one is actually the interesting one. And it says that although the algorithm never lets any arm go for good, again, anytime we say it's eliminated or removed or frozen, it's for one step only. But what happens is that any arm that, as per our definition, is non-competitive is going to be stopped being pulled after some finite time is reached. So we were able to show that those arms are pulled only finitely many times. The remaining arms that you cannot, even if you had infinitely many samples from the best arm, you couldn't narrow down your theta well enough that you could identify those as suboptimal arms. They are going to be competitive, and as in the usual classic bandit case, they will be pulled an order of log p times. So for those, we cannot provide any improvement. But put together, the result is still, in most cases, better than the classic bandit case, because instead of choosing all k-1 suboptimal arms an order of log p times, This is now reduced to C-1. And we will see examples with even real data where we see that like C tends to be, in at least some practical cases, much smaller than K. So from K times log T or K-1 times log T, reducing it to C-1 times log T is, in some cases, pretty substantial. And if you are lucky enough and C is 1, your case is particularly easy, or the structure is particularly well suited to this type of algorithm, C tends to be 1 and your regret is finite. So after some finite point is reached, you only choose the optimal arm. So that's sort of the highlighted result. There are no questions. I will continue.
So, actually, Osman, I had a quick question on that. So
Sure.
what were the distributional assumptions? You're assuming there's some sort of sub-Gaussian for every theta, or what's the?
Right. We assume they are sub-Gaussian with a given parameter alpha, and the results are for the case where alpha
Okay,
is
so that's the assumption that is known for every theta. You know that it's sub-Gaussian, and it is sub-Gaussian with that.
Yes, exactly. Right.
All right. No, thank you. Yeah.
Sure. Okay, so let's look at some simulation results. And as I promised, there will be some comparison with the algorithm that Latimore and co-authors proposed, the UCBS algorithm. There are a number of observations from this plot. First of all, it is for the same setting with 3 arms, just for simplicity. And in a moment, I'll talk about simulation results for the real data case. But the first thing to observe is that I am changing theta, the true value of the latent parameter, in 3 different cases. And this is done in such a way that in the first case, after the fact, knowing the problem structure, I can say that C theta is 1. So there's only one competitive arm. And in these cases, as I mentioned, our algorithm is expected to return finite regret. And blue results are from our algorithm. And as you see, after a finite point is reached, cumulative regret stabilizes. It becomes a constant, which means that the algorithm doesn't incur any further regret. So this kind of confirms that result. If C is 2, we expect to do better than, because it is less than 3, the number of arms, we expect to do better than the corresponding algorithm we are extending. And in each case, the blue being ours and red being the classical case, we can see that our algorithm actually returns less regret. In the last case, C is 3, so we don't necessarily expect to do better. We expect to do at least as good as the corresponding classic algorithm case. And the results show that we may have some minor improvements, but not necessarily as good as the other cases. The second comparison or second observation, major observation from this figure, is the comparison with UCBS. Just to be fair to this UCBS algorithm, we are just comparing for the moment its performance with our version of the UCB-like structured case. But you can see from these regret values that our TSC algorithm, for instance, does substantially better than in all cases their UCBS algorithm, maybe except this particular case. But what we can conclude from this figure is that UCBS algorithm may turn out to be the best, as in this case. It may turn out to be worse than our algorithm, but a little bit better than the classic UCB. But depending on the theta, it may perform even worse than the UCB that it is extending to the structured case. So if you are given a structure, technically you should never be doing worse than the classic bandit case. So UCBS doesn't follow this intuition, and depending on the true value of the theta, it can perform quite differently. To see this better, what we have done here is the plot with cumulative regret after a certain number of rounds has been played. So we took that sufficiently large, and we looked at the cumulative regret across different algorithms as a function of the hidden value theta. So if you think about it, what happens in reality is you are given the structure of the problem, but you are not told what the theta is. And you have to play one of these algorithms, and depending on where the theta lies, face one of these regret values associated with that theta. What we see is that UCBS is very sensitive to the true value of theta star. If you use it, Latimore's algorithm, you may end up doing actually the best possible regret, minimum possible regret among these 4 choices. But you may also do you may also be doing the worst possible performance. You may be observing the worst possible performance among these 4 if your actual theta happens to be here. So it turns out that the algorithm is too sensitive to a parameter that you cannot have any way of knowing ahead of the time. So one could argue that it is not, I guess, wise to use it, or it may be involving a little bit of uncertainty. Whereas the algorithms we propose always performs at least as good as the corresponding classic algorithm they are mimicking or they are extending. And in particular, you can see that the TSC, Thompson sampling version of our algorithm, across the board performs pretty much the best in all cases, except this, again, one specific case. So bottom line, the Latimore's approach is a bit too aggressive in making its decision. And as a result, in some cases, for some values of the true theta, it performs extremely well. But because of its aggressiveness, it can also be doing worse than a standard or classic bandit algorithm. So that's kind of the moral of the comparison with the Latimore's UCBS approach. So we extended the experiments to movie lens data set where we collected we are using a data set with 6,000 users, their ratings over roughly 4,000 movies. And the movies come from 18 different genres like comedy, musical, and so on and so forth. And this data set comes with some features of the users, such as their age and occupation. So we treat the hidden latent parameter theta, the context, as basically the age and occupation pair. And what we do is that we take the 50% of the data set to learn the mappings that our algorithm will be using, the mappings from theta to the mean rewards for each genre, and try to basically find the best possible genre for maybe a given theta, a age occupation pair, in a sequential way with the highest possible reward. And the rewards are here calculated in terms of the user ratings to different movies. The 18 different genres, we treat them as the arms or the choices that we are making. And the results are shown here, where we compared the classic UCB algorithm, the classic Thompson sampling algorithm with our versions, TSC and UCBC, and we again plot Latimore's UCBS algorithm as well. For 4 different theta values that represent 45 to 49-year-old clerical admin, 18 to 24-year college students, and etc. And one thing we observed that's worth noting here is that although we start with 18 arms, for these theta cases, the number of competitive arms is substantially smaller than 18. It's 6, 6, 3, and 1 in cases A, B, C, and D. So it's 6, 6, 3, and 1. And what this means is that as per our results, we expect to do substantially better than classic bandit algorithms. It means that a significant number of the genres will be stopped being pulled or shown to these users after some finite time is reached. And the main conclusion from these results is again similar. Thompson sampling structured case across the board seems to be the best performer. And in all cases, our UCB does at least as good as the classic UCB. Our Thompson sampling does at least as good as the classic Thompson sampling. And with respect to Latimore's approach, again, the conclusion is similar. In some cases, it is worse than our version of the UCB, but there are cases here again, it is ending up eventually being worse than our UCB structured case. But in those two C and D figures, it turns out to be better than our UCB structured algorithm. But again, the main approach or main contribution of our work is not to extend just UCB, but any algorithm, and therefore you are now able to use the Thompson sampling structured case. And if you do that, you are actually getting the best performance among those that we are using in this comparison. So that pretty much concludes the talk for the structured case. The key takeaways are that we are now able to provide a way to extend any classic bandit algorithm to the structured setting. And even the proofs for the regrets that we presented, almost 90% of it is done. It's kind of streamlined in the paper. So all you need to do is, if you have a new approach for the classic setting, you need to prove a specific result that we mentioned in the paper to get the regret result for your favorite algorithm for your future algorithm. So that we sort of view as the main sort of contribution of the work. The regret again is scaling like rather than k minus 1 times log t, it scales like t minus 1 times log t, and the non-competitive arms, put differently, are pulled only finitely many times. So that's the end of the first part of the talk, and I think the majority of the talk is about that. So I'll maybe take about 10 to 15 minutes for the other case, and that will be the end. But I can take any questions, I think, about structured case if there are any.
So just a quick thing. I mean, do you know what the lower bound here is? I mean,
well, that's the very good question that we couldn't answer. So unfortunately, I mean, there is a well-known lower bound for even the structured case, but unfortunately, it's given in a way that's not in explicit form. So you couldn't easily check. So I don't know how much you know about the bandit problems, but there is a way to prove the lower bound for the classic case. Mm-hmm. And the lower bound for the structured case kind of one by one tries to mimic that, and the result is provided in a way that says, if you solve this semi-definite programming, the result is going to be giving you the coefficient of the lower bound. But that's in most cases is, especially with number of arms being large, is almost impossible to solve. So we couldn't quite get a concrete answer as to whether.
At least for the problem where you had, I mean, the movie one is hard, but the first example, the simulation, were you able to get, I mean, there you could do a calculation there. Yeah. I'm just curious. Yeah.
So, yeah, it's a good question. So you are saying for this case, the lower bound could be established, right? Yeah. I'll double check and get back to you. Not that I am aware of, though. So, so one thing that we kind of observed was that those lower bounds, like there's a kind of well-known paper that has the lower bound for, they claim for any bandit setting. They say like it doesn't have to be fitting into any of the structured or non-structured case, any bandit setting, here's a way to get a lower bound. But they still fail to miss this case where you get bounded regret. So their lower bound is in the form where you say the regret is log t times something, and that something is always positive. So so the best known lower bound at least doesn't capture the finite regret case to the best of my knowledge. But I'll double check this simple case and see if there's an easily calculated lower bound and how well we do with respect to that. That's a good point.
Oh, sure.
Actually. Yeah. Okay. So the second part of the talk again is about correlated bandits, where we say we are looking at a population of users. Our recommendations are done one user at a time. And this population, you know, when I'm making a recommendation to a user, I don't know their context and I don't know the population distribution either. The context distribution of the population is not known. But what I'm trying to leverage is the fact that these rewards are correlated. I can estimate how much reward I would have obtained from this movie if I know that this user rated this movie in a specific way. So this is another way to show the same thing, and I specifically put my own picture to motivate or convince you the fact that these rewards are actually correlated. The argument is that if this user is myself, and if you tell me that I clicked on this particular advertisement with George Clooney on it, you can at least say that I have a pretty good chance of clicking the next one as well, because it's by all intents and purposes looking very, very similar, right? The same actor and, you know, holding a coffee and etc. And maybe if there were other items here that didn't look like coffee or they had a very different sort of framework, you could say maybe the upper bound is not going to be as tight, or you could say maybe the likelihood of clicking is not as large. So we are basically in this case leveraging the, trying to leverage in some way the correlations between different rewards at any given time. And once we are convinced that in a setting like this, where you get users one at a time and make one choice and then let them go, the question is, what can I assume reasonably about the correlations between rewards? And the first thing we notice is that you cannot learn these correlations under the assumptions posed unless you can pick this user and then show them multiple ads simultaneously, or keep them in the game and get their reaction to different items. There's no way of learning these correlations online. So we need to assume some sort of prior information. I believe actually the problem setting where you could show multiple arms to a user to learn maybe partially at least the correlations would be a very interesting setup as well, but we haven't studied that. For the moment, we are left with one feedback for one advertisement for each user, so we have to assume something a priori known if we want to make use of these correlations. And what we said is that let's assume the knowledge of upper bounds on the conditional mean rewards. So I don't want to assume anything about the distribution. And I don't want to assume anything about maybe specific users. All I want to assume is something like, what is the expected reward I would have gotten from one arm, given that another arm gave me this reward? And all I need is an upper bound. And the upper bound doesn't obviously have to be tight. The algorithm makes use of whatever bounds are given to it. And as tight as they are, the better results will be obtained, but there is no strict condition that they have to be all tight. So you can view this as a loose upper bound on something like, what are the chances that a user will like version 2, given that they like version 1? This is loose because if you think about it, this is talking about a specific user's chances of liking a version, but all I need is not per user, all I need is an average or an expectation about a user who likes version 1 and what are their likelihood of liking the second version. And again, all I need is an upper bound. So we thought this is pretty loose in terms of the assumption. And the question is, of course, well, you say it's loose, but how are you going to get that information? And again, domain knowledge is one example where you can say, domain knowledge or common sense, right? Like you can say, well, this is a coffee machine ad with George Clooney on it. This is a coffee machine ad with George Clooney on it. So there must be a correlation, a similarity. So you could use simple things like this. You could do a controlled user study again, bring people in and show them multiple options and try to learn these correlations. And the good thing about here is that as long as the rewards have a natural upper bound to them, let's say if it is reward is the click probability, natural upper bound would be 1. If it is movie rating, you could say, you know, depending on your scale, natural upper bound would be 5. You know, if you are using 5 out of 5 as the maximum rating a user can give to a movie. What this says is that if you have a survey result with some confidence intervals, you could convert those confidence intervals again to the upper bounds that, you know, hold with 100% probability for the conditional mean reward. So whenever you have a sort of estimation that comes with a known confidence bound or confidence interval, like you say 80% chance is there for this to happen, you could convert it to a upper bound as well in the form that we are you know, requiring in this model. And worst case, if you don't know anything, you are welcome to choose as your trivial upper bound the maximum value that the reward can take. So if you are using, again, movie star ratings, 5 is this sort of maximum value. If you put 5 here, you won't be wrong, right? The conditional mean reward will always be less than the maximum value that the reward can take. So yeah, that's kind of the setting, and we call these upper bounds as pseudo rewards. And the argument is going to be throughout the algorithm, and the discussion will be like, if I give the user this ad and I specifically observe a reward, let's say R1 is given R, I would treat this as I have pulled every single one of these other arms as well, and my rewards have been like this. So I will keep that information in the backup. So that gives me some sort of additional information about, in the upper bound form, but additional information about how much reward would I have obtained from these other possible choices that I could be actually choosing in the next run, and so on and so forth. Any questions about the model or concerns about the assumption? Yeah.
So no problem. I guess the bound is an almost sure bound, right? Yeah.
Say that again, please.
The upper bounds are almost sure bounds.
Right. I mean,
yeah.
Yes,
okay.
With probability 1, right? Almost sure. Yeah. So you can afford to have a measure 0 case not obeying the bound, right? Okay. So again, the argument that we like to make in this slide is that, let's say you ran a survey, you hired consultants, their domain knowledge helped you fill some of these tables, and whatever entries that you couldn't fill, like you couldn't figure out what happens if arm 1 returns 0 to arm 3, just fill them with the maximum possible value that, you know, your context dictates for the rewards to take. If all entries are missing, you are clueless about any of these mean rewards, you can fill all of them with the max possible. And we created an algorithm, a class of algorithms again, that will just perform exactly as the classic multi-arm bandit setting. So if you are using a UCB-like approach, filling all these entries with a trivial bound will not make you lose anything. You'll just recover the standard setting. Sorry. Okay, so the overview of the algorithm is quite similar with maybe minor differences with the structured setting. The first step, if you remember in the structured setting, was about creating some sort of confidence interval about a hidden parameter. Here we don't have any such hidden, so to speak, parameter. What we do is we first identify the set of arms from which we have enough samples. So enough in the sense of having T over K samples, where T is the current round we are in, K is the number of arms. And what you can see is that as time progresses, eventually only the best arm will be pulled this many times. Because even from the classic bandit setting, we remember that suboptimal arms are pulled on the order of log T times, which will be much smaller than T over K if K is finite. So this is a set of arms that initially starts with maybe having a number of arms. It doesn't have to be one, but eventually it becomes just the best arm. And the second step is about saying that let's eliminate some of the arms that we can perhaps guess that they are suboptimal. And again, this elimination is for one round. It's not a elimination for good. And this time we are doing it using this criterion. It basically says that an arm is empirically non-competitive at a given stage if its empirical mean pseudo reward is less than the mean reward of one of the arms in the set. So what this means is that for each arm, rather than looking at its own samples, I am looking at its pseudo reward. So from the samples of other arms within this set that have been sufficiently sampled, I'm looking at, from the results of those samples, what conditional mean upper bounds are provided to me, and using the minimum of those, and eventually this will become a true, with almost sure guarantees, upper bound on the reward of the arm that I am talking about. And if this natural upper bound is already less than or equal to the mean reward of some other arm, what you say is that, well, this guy's upper bound is less than the mean reward of this one. So upper bound less than this means that there's a good indication that this one is suboptimal. So we say that for this round, you are frozen. You don't continue to the next step. In the next step, we again borrow any classical algorithm of your choice, UCB, Thompson sampling, etc. are possible. And we basically, for this algorithm as well, have similar guarantees. The competitive arms, I mean, this is expected, but non-competitive arms are pulled again order of 1 time. And the notion of non-competitiveness is again very similar. If you can identify an arm as non-competitive by pulling only the best arm with enough samples from the best arm, if you can tell that it is suboptimal, they will be non-competitive. But this time it will take a different approach. So if you get sufficient samples from the best arm, you'll get pseudo rewards. Like from this arm's results, you will have upper bounds for all the other arms. So if upper bounds are tight enough that lets you say, well, these are definitely not optimal, you are able to, with this algorithm, stop pulling them in finite time. Therefore, expected regret again scales like C-1 times order of log t. And there are cases again where C is 1, in which case the regret of this algorithm will be order 1. The number of competitive arms, again, the definition is repeated here. It is non-competitive if its expected pseudo reward with respect to the best arm, K star, is less than the expected reward of K star. So using only the samples from the best arm, you have a good idea about an upper bound on the rewards of other arms. These upper bounds, some of them are not tight, so they tend to be loose, and they actually tell you the upper bound is actually above the reward that you see from the best arm. So in those cases, you are competitive. But if your upper bound is less than or equal to, so this is the definition for competitiveness, but if your upper bound is less than or equal to the best arm's mean, then you could be eliminated in finite time. So you are non-competitive in those cases. So the results are, again, simulation results demonstrate this. Like when C is 1, number of competitive arms is 1, we can show bounded regret. And if number of arms is 2, rather than the number of arms K being 3, we still get an improvement. So CUCB and CTS, the triangle here and the cross here, are our algorithms, and they are trying to mimic or translate. In the blue circles case, it is mimicking the UCB, so, and improving the regret over that. And in the Thompson sampling case, the comparison, fair comparison, is with these gold circles. So it is again improving the regret significantly. But there are cases, of course, where everybody's competitive. Your bonds are not tight enough that you cannot improve. the corresponding results, what we see is that we still match, the algorithm that we are mimicking. So you can safely use this approach. Worst case, you will do as good as the classic bandit algorithm. And again, we repeated the movie lens experiment. And this time it was a bit non-trivial to maybe fit that data set to the framework that we have. What we have done is to be able to say that some of these bounds may be loose. We said that, okay, let's look at again 50% of the data set, calculate some of these conditional mean rewards, but then eliminate, assume the data is lost or some of the entries have been by mistake maybe replaced. So we say p fraction of the data set is replaced by the trivial bounds. So in this case, movies can take at most 5 as their rating. So p fraction of the data set is basically made useless in some sense. The trivial upper bound is used. And what we see is that even if p is 70%, so we take the data set, we have sort of upper bounds for conditional mean rewards, but 70% of them are then just replaced with trivial results. Even then we can see relatively substantial improvement with our algorithms as compared to the classic setting. So even if these correlations are not at all tight, like 70% of them are trivial, the remaining 30% is going to give you useful enough information that some of the choices are stopped being pulled in finite time, and overall your regret becomes substantially smaller than what you would have obtained if you just ignored those correlations and used the classic bandit algorithm. So that's kind of the conclusion from these plots. The key takeaways are similar. We are able to translate any classic bandit algorithm to this specific correlated bandit case. And the corresponding regret scales like c minus 1 times log t rather than k minus 1 times log t. One thing I didn't have time to talk about here is the best time identification problem. So there the goal is not to worry about the regrets, but you are saying, I want to know which of these actions return the highest mean reward, so which one is the best. And I want to decide this using as few samples as possible. I don't care how much regret I have, how much reward I get in the process, just look at the number of samples. And we recently came up with a way of actually solving the best time identification problem in this correlated bandit case. And there's an upcoming paper on that soon. I think we will upload it in our archive. And for the structured bandit case, actually the best time identification is still an open problem. So that ends my talk. Hopefully I didn't go too long over the time limit, but thank you for listening, and happy to take any questions.
Running late, it's actually gone quite a bit further out. So let me do one thing. So we had 2 discussants, maybe. So just have Baekjin, if you want to quickly talk about it, maybe instead of 5-6 minutes, if you're just going to present for like 2-3 minutes, we can go through.
Okay, sounds great.
Quickly. Yeah, and then Shin, you can do the same as well.
Yeah, okay. Let me share my screen, please.
Just a second.
Yep. I'm Baekjin from State Department, and thanks for sharing your interesting work with us. So I will skip the summary. Yeah. So for
that's good. Yeah, please.
Yeah. Here is some comment. So both correlated bandit and algorithm competitive are flexible in choosing any classical bandit algorithm in terms of the theoretical and computational aspect. And in structural bandit, this problem setting does not make any assumption on mean reward functions, so that it can subsume several existing frameworks such as linear bandit and generalized linear bandit. And for correlated bandit, at first glance, the assumption that pseudo rewards are given as a prior knowledge seems quite unrealistic in practice, though they can be obtained through the domain knowledge or survey. But a key advantage of this framework is that pseudo rewards are just any upper bounds on the conditional expected rewards, and thus not necessarily to be the type. Is it correct? So this loose upper bound can be obtained even with small number of data set. Yeah, that is the comment. And
That's correct.
I have two questions in the structure arm setting. So other than linear reward or generalized linear reward, the assumption that reward function for arms are given as a priori might be unrealistic in practice. So if the hidden parameter theta star is univariate or very low dimensional, then some density estimation technique can be applied to offline data set. But you already partially answered this question. Is there any real world application where each reward function can be easily accessible or estimated? And another question is the computational complexity of the algorithm C heavily depends on the construction of the theta T hat and identifying the theta hat T competitive ones, right? So
Right.
if the primary space theta is high dimensional, then discretization idea might not work well. So if linear structure in reward is considered in high dimension, then like a lasso bandit was proposed based on the sparsity assumption or penalized regression by fully utilizing the linear structure. But is there any idea on how to improve the computational complexity in high dimension or exploit the sparsity assumption in the setting that you study? Yeah.
See, so the first question I think is, so the mean reward functions, I think, yeah, the examples that we have seen was like, if you have sufficiently large number of users rating movies, I think the mean, so again, we are not assuming that the distribution is known. So there are some works that assume even the exact distribution from theta to the mean is known, but from theta to the reward is known, but we are not making this assumption. We are just simply saying that the mean reward is known. And it's basically, I would say, real world application will boil down to the law of large numbers, right? If you have enough samples, enough number of users from the same theta ranking a set of movies, their average will be very close to the mean, right? As long as the number is large. So another thing we discussed briefly among ourselves was like, what happens if the mean functions are not accurate, but they are like given with some noise, maybe there is some uncertainty in the mean. So those cases I think could still be handled. So our approach was that, or our intuitive idea, we haven't worked on it, was that if you know the mean within some error, you can still convert that to an estimation and a confidence interval on theta from your samples, and then still use an approach like ours. And then, I mean, all you need is basically you have to loosen some of your criteria and say that if the upper bound of your mean is lower than the lower bound of the others, then you can freeze that arm. So you have to maybe lose from the performance, but you can avoid at least making mistakes. So my answer to the question is it depends. It may not be easy as you suggested, but it's certainly a much less stringent assumption than assuming that the conditional distributions are known. The second one I'm not too sure about actually, like what are the computational costs in high dimensions and how can we exploit sparsity? I'll think about it and get back to you on that. I'm not too sure if, yeah, if the theta is high dimensional, I mean, I agree with you that some of these can be extremely intensive computation-wise to complete the steps of the algorithm, and without linearity, maybe the sparsity assumption is not as easy to sort of exploit. Yeah, but it's a good question. I'll think about it. Yeah.
Yep. Thank you. Thanks for your talk.
Thank you.
So, Shin, if you're there, if you want to go just very quickly, if you have a few questions, if you want to just mention that, please go ahead. Yeah.
Yeah, sure. Okay, first I'd like to thank Osman for a very nice talk and for these two nice papers. And I will skip also the summaries and just go into the discussions, questions. So for all of the theoretical results, we saw that they are about the instance dependent regret. So I'm wondering, like, is it straightforward to extend this instant dependent reward to like instant independent reward, like the classical one? So yeah, so this is like the upper bound is this one, or we can get the lower bound on like square root of c times t, and that's it for the first question. And the second one is that can we characterize the this so-called competitive set C with that, like the set information? So for example, if we have like the IID arms, then the C is just the honored arms, the K. And if we given full distribution of the arms, then the C will become 1. And also the last question is that what if we know the use features? So these techniques used in these two papers are still valid? And also, if we have this kind of feature information, can this regret bound be improved? Yeah, thank you.
Right. The first question, I think the answer is still open. Like for the instance independent regret, to the best of my knowledge, there is no result that says it's going to be given as a function of the number of competitive arms.
Okay.
That's a good open direction to pursue. I think we haven't looked at instance independent bounds for the regret, and sounds like you should be able to get a result that's in some sense looking like the ones that you suggested, that there's some explicit dependence on the number of competitive arms, but yeah, there's this is an open question.
Okay, got it.
As far as I know. The second question says competitive set explicitly with side information. So I can, if I know the problem, like the reward mappings, and I know the theta, I can exactly tell you what the set of competitive arms is.
Mm-hmm.
But are you looking something more explicit, right? So
yes,
it's really about like you have to take the inverse mapping. So the way to know is it like you look at the best arm and look at the specific theta value. Again, it's sort of so the way you said is like two extreme cases where even if you don't know what the theta is, there's a specific answer for the number of competitive arms. But for interesting cases, even when the reward mappings are known, the number of competitive arms will still be different for different realization of the different actual value of the latent parameter. So that won't be an explicit thing that comes directly with the mapping. But what you can do is identify the reward mappings, find which theta you are interested in, and for this theta, identify the best arm. And then the question is, are there other theta values that this best arm taking similar close reward values to the best reward that it is achieving at that theta? And basically, the confidence region on the theta is going to be your operating region, and then you'll check if other algorithm, other arms, I'm sorry, have at any of these theta values have a better reward than the one that you identified as the one. If not, they are deemed non-competitive. So it's kind of a manual operation that you need to follow a number of steps to identify. So I don't think it will be as simple as nice as you are suggesting, except the trivial cases, of course. Yeah. And if you know the user context, there is a huge literature on contextual bandits. But in our setting, if you know theta, then the problem is done because you assume the mean rewards are known, and you can just identify the best one. So that I'm assuming you are asking for the case where you know the context, but you don't know the mean reward mappings. So if you search for contextual bandit algorithms, there the idea is theta is not fixed there necessarily, right? So every user comes with their own theta and users come one at a time. The goal there is to learn those mappings in some sense, or more precisely for each theta, identify the arm that performs the best. And over time, if you learn that, what happens is for each user comes in, you give them a different choice. So in that context, there is no best arm in the usual like uniform sense. There is a best arm for each context, and you're trying to identify that. So our techniques, I don't think, are directly related or applicable. So
Okay.
yeah, that's my answer to the first.
Okay, cool.
Couple
Okay.
Thanks a lot, Osman. So I think maybe we should stop
Thank you.
now. Thanks again
Okay.
for the seminar, and thanks for the discussions for all the questions. All right. Good luck. And thanks, you're meeting a few people tomorrow as well. Thank you.
Right. Thank
Bye.
you. Thank
Thank
you so
you.
much. Sorry for going too much over time.
Oh, no, that's okay. We don't mind.
Okay. Thank you.